Okay, welcome back. In the last lecture, we derived what is known in the literature as the Vig Theorem. And the Vig Theorem, from our statistical field theory standpoint, is just a prescription to evaluate endpoint correlation functions of a theory with a quadratic Hamiltonian in the fields. So essentially, our object are thermal averages of even products of fields in n different points, where n is actually, say, 2i plus 1, meaning 2i is an even number, in a theory which we will denote as naught, to remind myself that h naught is not any Hamiltonian, but it's actually a quadratic Hamiltonian, where W is some general operator which doesn't depend on fields, and therefore the Hamiltonian is a nonlinear functional of the fields. And what the Vig theorem says, well, first of all, we can graphically represent these correlation functions as a blob to which we connect n legs. So this is x1, this is x2, x3, and this is xn. Okay. And what the Vig theorem states is that you can evaluate this correlation function by summing up all possible ways in which you can contract the n points of the correlation functions by drawing lines between them. Now, since the correlation function of a Gaussian theorem, or of a Gaussian Hamiltonian, or a quadratic Hamiltonian, is 0 for odd number of points, so for 3, 1, 5, 7 fields, and is non-zero only for even number of fields, you can always connect the points of a non-trivial correlation functions with line. So for instance, 4-point correlation functions, which is the one that we evaluated last time, gives rise to 3 different diagrams. By this joint here, I mean that this line do not touch. I chose not to draw this diagram this way because, as we shall see in a couple of lectures, this, in the language of field theory, involves a quartic contribution to the Hamiltonian, which we are assuming we don't have in our calculation. So to distinguish this situation, which is not happening in the free theory, to the one that we discussed, we draw 2 lines and a little bridge to suggest that the 2 lines don't touch each other. And so let's make an example and see what happens if we want to compute higher order correlation functions. For instance, we want to compute a 6th order correlation function. So now we have 6 points, 1, 2, 3, 4, 5, 6, and then they're all connected to the same blob. This is my 6-point correlation function, and if I apply Vig theorem, I have a certain number of diagrams to count. For instance, I have this. So let's say 1, 2, 3, 4, 5, 6. Then I have, for instance, this, and this. And then I have many others. How many diagrams, how many different ways of contracting the indices? So using a terminology that is proper of field theory, how many contractions do I have? Well, let's look. When I pick up the first point in this 6-point correlation function, I have essentially 5 choices to connect it to. Suppose I chose one, then I have to choose another point, and then I'm remaining 5 minus 1 choices, and this gives me very easily you can imagine that this gives me a factorial number of contractions. So the order of contraction is a factorial number. So very soon you come to a regime where the order of the correlation function becomes very large, and you have to sum a large number of quantities. Now, if you're computing thermal averages and your quantities are positive definite, as normally you find the case, well, this is not a big deal. The problem arises where all these different contractions have a different sign, an alternating sign, so to say. In which case you have a large number of quantities being summed with different signs, giving rise to a result that is typically small compared to the individual value of all the quantities you're summing. This is exactly the kind of situation where you don't want to be, because you're summing many quantities on which you in principle have an error, and the sum is a small number. This is what happens when you compute correlation functions of fermions, and this is the origin of the sign problem from the field theory point of view. But this is not the subject of this course, and I leave it for the quantum many-body course or for the quantum field theory course. But as far as us is concerned, the fact that we have a factorial number of diagrams or contractions is not a big issue. Now, what can we do with the quadratic theory? Very little, in fact, right? I mean, we have solved the three theory, and we discussed that this is basically an infinite dimensional generalization of solving the harmonic oscillator, which is an important problem, but you know, there's quite a finite amount of physics you can do with the harmonic oscillator alone. So really, the Hamiltonians that we are interested in are in general non-quadratic. When we talk about, you know, spin systems, as we discussed as a prototypical example, quadratic Hamiltonians are good only for the paramagnetic phase. But already, if you want to study ferromagnetic phase and ferromagnetic phase transition, you want to go towards Landau theory, you need to incorporate at least quartic terms into the Hamiltonian, which tells us that basically the tools we have developed at this point are not sufficient to cover an acceptable wide range of physical systems. So the real question that is at the heart of theoretical physics, if you want, is how to solve. Nonlinear theory. Now, I'm using the word nonlinear, even if in mind we have a quadratic Hamiltonian. So when you speak about nonlinearity in physics, normally you refer to the equations of motion, not to the Hamiltonian. So if you have a quadratic Hamiltonian, the equations of motion, at least at the classical level, are linear. Think about the harmonic oscillator. You have a quadratic Hamiltonian, but then the Newtonian force is linear in the variable. So typically, nonlinear theory means theory with more than quadratic in the Hamiltonian. Now, a few lectures ago, I was mentioning provocatory statements that I like to say, that basically we can do two things in mathematics which enable the existence of theoretical physics, without which there will be no theoretical physics. We can solve Gaussian integrals, and we can perform Taylor expansion. If we didn't have any of these two tools, we wouldn't be able to do any calculation at all, almost, in theoretical physics. And, we would be stuck to trivial problems in elementary physics classes. So in the last lecture, we saw that solving Gaussian integral is the key to solve for quadratic Hamiltonians. Of course, now we are left with basically one tool, that is the Taylor expansion. And I would say we also have stochastic methods, as we shall see, as a secondary arrow to throw in our arch. So really, the question of solving for the Hamiltonian uh, is really finding techniques to find, if not exact, at least approximate solutions. And from your background in um, in quantum mechanics, for instance, we know that the first natural thing to think of to extend the solvability of a theory beyond the linear regime is to invoke perturbation theory. But in this lecture, I will not derive perturbation theory in field theory. I will do it in the next lecture, and we'll derive Feynman diagrams techniques. In this lecture, I want to do some general discussion about perturbation theory, because I believe perturbation theory often is overlooked. So let's go back to what we are typically taught in quantum mechanical course. We say, okay, we have an Hamiltonian that is consisting of two terms. One Hamiltonian that we call the unperturbed Hamiltonian, which we assume we are able to solve. Plus, you have a perturbation, and we assume the perturbation depends on a small parameter. And typically, perturbation theory tells you, okay, if you can diagonalize the perturbed Hamiltonian, then you have a way to approximate both the eigenvalues and the eigenstates of the full Hamiltonian, provided that the lambda parameter that sits there is small. That is, in a nutshell, what perturbation theory is all about. For instance, if we want, the corrections to non-degenerate states, for simplicity, say to the ground state, what you have to do is to evaluate the expectation value in that state of the perturbation. And then if we want to go beyond leading order perturbation theory, you have a sum over all states. And we saw that at the beginning of the course. Now, that's all clear, except that it's very, very difficult to make sense of it. So let me give you some example why all this looks okay, looks clear, but when you give it a little thinking, it becomes far from trivial. Let's begin by considering the fact that in many cases, the Hamiltonian contains physically dimensionful perturbations. Now, when you have a dimensionful perturbation, how can you tell whether it's small or large? Of course, you need a dimensionless parameter to claim that this parameter is actually small or large. But for instance, if you were in a situation where your unperturbed Hamiltonian was, say, the harmonic oscillator Hamiltonian, and your perturbation was a quartic term, let's say k 4x to the 4. Now, clearly, this guy has to have the dimension of an energy. But x has the dimension of a length, of course, which means that k has the dimension of an energy divided length to the fourth. Can you say it's small or large? It really depends on your units, right? So what you really want to say is that the correction to the energy divided by the unperturbed value, this is a dimensionless parameter, and it's smaller than 1, for instance. So perturbation theory really works not when the coupling constant per se is small, but when the effect of the coupling is small, which is something you evaluate a posteriori. So typically, you do your calculation, get your result, and then compare the perturbed and unperturbed result. And as long as your perturbed perturbation corrections is small compared to the unperturbed result, then you're happy and you declare that your perturbation theory works. Now, very often, the smallness of the perturbation is a consequence of a non-trivial interplay between the essential scales of the problem and the couplings of the problem. For instance, your particle, what the scale k is doing here is telling you how steep is the quartic component of the potential energy landscape, providing an effective length scale for confinement of your particle. And that scale is related to the typical size length scales of an harmonic oscillator, and the ratios between these two determines whether you have a small or a large perturbation. So a perturbative theory cannot be easily inferred unless you do the calculation. There are situations, however, where you have a perturbation theory is defined in terms of a dimensionless parameter. And the typical case are renormalizable field theories. And an example that everybody probably has seen is quantum electrodynamics, or will see or has heard about. In quantum electrodynamics, the expansion parameter is the fine structure constant, which is e squared over 4 pi. Now, if you don't come from a quantum field theory course background, this is the same expansion parameter that determines the correction to the ground state of the harmonic of the, say, hydrogen atom wave function when you start including hyperfine corrections. So there are situations in which this parameter appears even without having to invoke quantum field theory. But when you compute, say, the scattering of an electron or of a positron by exchanging a photon, typical QED problem, then your cross-section will be proportional to alpha. And people say, wow, fantastic, QED is perturbative because if I work out this number in natural units, this number is 1 over 137. That's a small number. It's a small dimensional number. Therefore, I expect to have perturbation theory working beautifully. So, however, we all know that an hydrogen atom exists. An hydrogen atom is a bound state of an electron and positron. Well, there's no way you can start from unperturbed states that are plane waves and perturb them and get a bound state, right? That's the pole in the correlation function. Stated differently, it's a nonlinear contribution to the correlation functions. Non-analytic contribution, poles to correlation functions, to Green functions. So the existence of bound states is a completely non-perturbative effect. And the existence of a hydrogen atom is a consequence of QED. So here comes the question. How come you told me QED was perturbative, and now you tell me there is an hydrogen atom which is a result of a non-perturbative interaction? So the fact that you have a small dimensionless parameter in the Hamiltonian doesn't necessarily mean that anything you want to compute can be computed in perturbation theory. In QED, you have a small dimensional parameter, but you don't get the hydrogen atom from perturbation theory. So QED is both perturbative and non-perturbative because there are aspects of QED that are not following from perturbation theory. There's no way you can exchange one photon between the proton and the electron and obtain an hydrogen atom wave function. And in fact, if you want an answer to this apparent paradox, let me just give you the idea. Normally in QED you use perturbation theory when you study scattering problem, because during scattering problem, because of the Born approximation essentially, you have only very few photons that can be exchanged during the scattering. And each photon exchange comes with alpha, and therefore you expect that to give you a small correction. But when you have a proton and electron sitting close together, they have time to exchange an infinite number of photons. And so anytime they exchange of photons, you have a contribution that is 1 over 137. At the moment you exchange 137 photons, you have corrections of order 1. So a bound state is something where you have two particles sitting close, interacting forever, and you'll now see that there's an additional scale that sets in, and is how long these two particles have been interacting with, which is responsible for the applicability or not applicability of perturbation theory. So all this discussion is supposed not to clarify doubts in your mind, but to raise doubts in your mind. I want you to think critically about perturbation theory, not as a standard tool that you can easily apply simply because you see that your Hamiltonian has a small parameter, but really something you learn a posteriori whether you could have applied it or not. And problem by problem, or families of problems by families of problems. Last but not least, even when you can do perturbation theory in field theory, bad news, the perturbative series is not convergent. It's only asymptotic. So if you really examine all the diagram, all the corrections in perturbation theory, you will not get infinitely close to the right result. You will get arbitrarily far from the right result. Typically, asymptotic series are series that get close to a number, they stay there for a while, and then they depart again. And perturbative expressions are like that. So there are sorts of complications in field theory, and we will not enter those complications. What I will be doing here is simply give you tools to get perturbative corrections. But it's your responsibility at the end of the calculation to take your results, compare with the unperturbed results, and decide whether you can trust or not trust your perturbation calculation. If you want, all the discussion that I had so far, which arises many doubts, probably sounds confusing, but it basically aims to say, don't use perturbation theory blindly. Do the calculations, and after you're done, go back and a posteriori assess the viability of the calculation you've done. And I want to close this discussion by giving you the typical example that I stopped asking in exams because I was failing students on the same question over and over. So I decided that I would be part of my lecture. Suppose we have a set of data, experimental data, that we want to reproduce in a theoretical calculation. Say, at some value of momentum, you have some kind of value observable. This is the experiment. Now, suppose this is observable of order 1 and this is 0. Suppose you first do your calculation in your unperturbed Hamiltonian and you get this theoretical prediction here. Next, you say, okay, this is not very good. I need to go beyond. And then you start doing perturbation theory. You perturb this calculation by adding the missing part of the Hamiltonian and see what you get. And suppose you get this. What do you conclude? Many of you might say, fine, perturbation is doing very well, because by including the effect of perturbation, I now agree with the experimental data. And this would be wrong. Even if my perturbed calculation agrees with the experimental data, the correction that I bring in by perturbation theory is as large as the unperturbed result. Which means that my perturbation theory is getting the right result by pure chance, not because it accounts for the right physics. It is just a coincidence, and I should not trust this agreement whatsoever. This is just a coincidence that I get, and it's a coincidence that I get the right result. Okay? So, this theory, this lecture, once again, is not about you to be able to do things with a clearer mind. It is just to raise doubts in your mind that you should be careful in trusting the results of perturbation theory. In the next lecture, I will actually derive perturbation theory for the quartic theory for you. And we'll do some calculations. Okay, bye-bye.